Hi everyone, welcome to 4250 or 8250, Design and Application of Lasers. I'm your instructor, Dr. TJ Hammond. This week we'll be covering Chapter 4 from your textbook, Laser Physics. That covers laser oscillation, gain and threshold. For Monday's lecture, what we'll be covering is the gain equation. So why are we covering this? Well, the two main points of interest in lasers are the fact that the A stands for amplification, as in we can make something very, very bright. And the SE stands for stimulated emission, as in we can produce light in phase, or make it coherent. And we can stimulate this emission, of course. So this week we'll be dealing with the amplification by stimulated emission. So basically the most important part of lasers. So this setup would be called ASE, so amplified spontaneous emission. It's not quite a laser, but it kinda is. Okay, remember what we need for a laser is an energy source and something to convert that energy and amplify the light. And that's basically what we have here. So we have this green big arrow that's pumping in energy to this thing here, this blob of matter that we're going to call our gain medium. So we still have to obey the laws of thermodynamics, so we don't just get amplification from nothing. So we still need this energy source, and then this gain medium converts that energy source, whether it's light or some voltage or something like that, it converts that to some light, to some radiation, to some light, typically in the visible or near infrared. So this gain medium, we've pumped some atom somewhere in this thing, and this thing spontaneously decays. As we've said, we looked at in the past few weeks, if we excite an atom up to some excited state, this thing can spontaneously decay. But of course, this has to release a photon, right? So this releases a photon, and right now we have no preferential direction for where this photon is going to go. So it goes off in any direction. So some atom that gets excited over here, this thing flies off, to the top left. Some atom over here flies off this way. Some atom over here. This photon that it releases ends up flying this way. This way, this way, this way. So it ends up releasing in just any random direction. Of course, some from over here can go that way. Everything like that. They're going off in all random directions. But if we happen to have a photon over here that gets emitted in the horizontal direction to the right, so this atom takes some energy from this energy source, creates this excited population state. So say if it were a hydrogen atom, it goes from 1s to 2p, for example. Then this thing spontaneously decays, but it happens to spontaneously decay right along this gain medium direction. Well, eventually it's going to hit some other atoms that are in the excited state. So now it's hit this atom in this excited state, and so now it's going to release a photon of the same energy and phase, and then that photon is going to continue, and then eventually, it's going to continue along this gain medium, and there's going to be more photons. This photon is going to hit some other atom that's going to release a photon, and this photon is going to hit another atom and release another photon. So we're going to get this amplification off to the right. So because it started on the far left side, it gets amplified as it goes to the right. And so this is called ASE, it's amplified spontaneous emission. So this light is coherent, and it's coherent with this photon that we started off with, okay? So that's why I say it's kind of like a laser, because we get this amplification. It's amplification by stimulated emission. But the thing that's missing is we don't have all the parts of a laser yet. And because we don't have all the parts of the laser yet, this photon could have also come from the right, and it could be going to the left. And so in the first slide here, we have light going off to the right, but in this slide here, we get amplified light going off to the left. And so you can see that this is going to be equally going off to the right, to the left. This photon could have started from the middle, and it could have been going to the right, or it could have been going from the middle and going to the left. And so you end up with this, the amplified light is coherent with this initial photon, but the thing is that on average, there isn't going to be this coherence. You're not going to be able to see, so some other random photon that ends up releasing here and gets amplified isn't going to be coherent with this photon, and so you don't have that true coherence that you get from a laser. So ASE, as I say, is exponential growth. It's an exponential growth process. And this will be an assignment problem of plotting an exponential growth process. But this exponential growth happens just like viruses, bacteria, and humans. I'm sure you guys might have noticed that at the beginning of this COVID epidemic, you saw that there was exponential growth in the number of COVID cases. So something that is proportional to the number of things you already had before is going to lead to some kind of exponential growth. So what we have is any intensity that's going to the right, so we'll say I call that I plus, and so the rate of change of I plus, the intensity of this beam to the right, or the number of photons that's going to the right, is going to be proportional to the number of photons. So that gives you this rate equation of di by dz in the right direction is equal to g, and g is this gain coefficient times the number of photons that are going to the right. Okay? So from such a laser that only has like one pass where it goes once to the left or once to the right, how much do we actually get for such a laser? So if we have a normal gain coefficient of about 0.01 inverse centimeters, that's nothing too, that's kind of like a normal gain coefficient. It's nothing too exceptional, but it's like fine. If you were to have a gain coefficient of that number, then you would have a laser gain medium, say if this thing's a meter long, if this thing were like a solid state laser, so it'd be like a piece of glass. This thing would be in like a really long stretched out tube. It would be called a laser rod. That's kind of the nomenclature for that. But you had this laser rod that's 1 meter long and it had this gain coefficient of 0.01 inverse centimeters. Then of course, this is an exponential function. So we have e to the 0.01 inverse centimeters times e to the 100 centimeters is going to be e to the 1, and that's 2.7. So that means we get a gain of this photon that started here that comes out this end here, and it's a meter long, and we only get 3 times the number of photons that we started off with. So who really cares? That's not really that big of a deal. Well, the thing is that that's not an entire laser, right? This is just the energy source and the gain medium. We also need this to be in a proper laser setup, and that requires these mirrors. So if you remember that from one of the first days, we were talking about the entire mirror cavity, or the entire laser cavity. We also need to have these end mirrors. So we need to have some kind of feedback. So the light goes out to the right and then reflects back, comes back to the left, and then comes back and forth and back and forth. And that feedback is what actually gives us this coherence. So on the left, we have a highly reflecting mirror, and this will be at z equals 0. So this cavity length has some length z equals L. And so on the left mirror, we're just at z equals 0, and on the right, we're at z equals L. And this mirror on the right will be slightly less highly reflecting. Okay, so these mirrors allow for feedback. So let's look at these mirrors a little more closely. The mirror on the left we'll call R1, T1, and S1, where R1 is the reflection coefficient, T1 is the transmission coefficient, and S1 is the scattering coefficient. So typically you want to have your mirrors as clean as possible, and so you want your S, the scattering, which is just like if you had like a dust particle on there or something like that, or some pockmark on your mirror, you really don't want those kind of imperfections, and so you want S to be as close to 0 as possible. So that means that so we'll just say that S is basically 0 for now, and so we'll say that the total intensity of the light is going to be, the reflection plus the transmission is going to equal 1, okay? Or the relative total intensity of light. So that means that if a little bit of, if the reflection is say like 99.99%, then that means that 0.01% of light would leak out through this mirror. Now we have on the right a slightly less highly reflecting mirror, and that's what we're going to call our output coupler, or a mirror that allows some light to outcouple from this laser cavity. And so this transmission will be T2, and so the intensity out of this laser on the right-hand side will be the intensity of this light propagating to the right times T2. And so the reflection coefficient will be R2, the transmission coefficient will be T2, and the scattering coefficient will be S2, but again, the scattering coefficient will be close to 0. So as a note, your textbook uses little letters R, T, and S. But the problem is that eventually we'll be getting to, we'll be trying to calculate the field reflection and the field transmission. And then it gets a little complicated because then you'll have R and T still. And so I want to distinguish between reflection coefficients, which deal with transmission, and field and the reflectivity and the transmittivity of a mirror, which deal with the field. So you just have to be a little bit careful of how we describe that when you're dealing with a field, which is, proportional to the square root of the intensity. Okay, now when we put this gain medium in between these mirrors, how does that make it work? How does that allow this laser to work? Well, I've taken out this energy source, but we're still pumping this gain medium with some energy source. This gain medium is still, spitting out photons in all directions, but these mirrors only allow feedback of the photons that go along in this horizontal direction. Anything that goes off this way doesn't get amplified, right? But anything that goes off to the left will bounce off this mirror and come back to the right, and then that could get amplified through here. Come to this mirror, most of it will get bounced back to the left and then get further amplified here. And so that will be that feedback mechanism that's required in order to get this laser to work. So we'll be going through the math more closely in class, but it's effectively that for the steady state solution, so for the amount of intensity that's going to be lost versus the amount of intensity that's going to be gained, or the number of photons that are lost versus the number of photons that are gained by each cycle of this, this light making it through the cavity, will be R1 times R2 times the exponential of 2GL is equal to 1. So that's 2 times the gain times the length of this cavity. Okay, so that's steady state. So it's not gaining further intensity, it's not losing intensity. This is just what it is, when it's, when it's a steady state. So now we can solve for this gain at threshold when this is equal to 1. And so we take the log of that, and so we get that the gain at threshold is -1 over 2L times the log of R1 times R2. Now, the log of R1 times R2 when R1 and R2 are very close to 1 is, you can simplify this to be the gain is 1 over 2 times the length of this laser cavity times 1 minus R1 R2. So this is true if R1 times R2 is around 0.9 or so. 0.95, 0.9, which is typically what lasers are set up. So this reflection here is typically on percentage 99.99% or 0.9999, whereas this thing here might be like 95% reflection, so 5% transmitting, so 0.95 or something like that. Those are kind of typical laser numbers. And so that kind of satisfies this approximation here. Now, if your laser gain length isn't the length of your cavity, so your cavity could be really, really long, several meters long, and your laser gain medium could be several millimeters. So in the first class, I talked about dye lasers, where you just have a jet. A jet is only going to be 1 millimeter too thick, but your cavity is going to be something like 2 or 3 meters long. So you can have a laser gain length that's substantially different from your cavity length. But in that case, there's just a very slight modification that instead of being -1 over 2 capital L, the entire length of the cavity is just over 2L, the length of this gain medium, and that's the only difference. Okay, so that gives us our gain from our threshold, which is the amount of gain we would need in order to make sure that this thing reaches some steady state solution, so that we have a constant intensity or a constant energy out of this laser. So when you have like a diode laser and you're pointing this, as a laser pointer or something like that across the room, that amplitude is basically constant, and so that means that you've reached that steady state solution because it's not increasing or decreasing in power or in intensity. Okay, in this lecture, we're also going to talk about the photon rate equation. I'll get a little bit more into this in the lecture, but basically, if we have to include time-dependent phenomenon to our photon numbers that are rattling around within our cavity. So if we had some kind of time-dependent process, like say if we just turned on the laser or something like that, then we also have to include time. And so before we had just the partial derivative with respect to space is equal to this gain times the intensity. But now we also have 1 over c times the partial derivative of the intensity with respect to time. So your daily assignment for Wednesday will actually be reading through the textbook to try and, or you can just sit and think about this, justifying where this equation comes from. So last week I spent a lot of time talking about the electromagnetic wave equation, or just wave equations in general, and that was a second order derivative with respect to space and a second order derivative with respect to time, with 1 over c squared being the velocity of this light. But now we have intensity, and now that we have intensity, we only have a first order partial differential equation in space and in time, and they are again related by c. So I'll have you let you think about that, justify this, see if it's right, see if it's wrong, and that will be it for Monday's lecture. That will lead us into talking about 3-level and 4-level lasers, where we can actually talk about how to analyze the state level population levels in actual physical lasers. All right, and that's it for today.